Hi, in this lecture, we start off with chapter 3, which is partial differentiation. Partial differentiation is actually motivated, or rather, what we will be doing with partial differentiation, we will be finding derivatives of functions of several variables. So that means that a function of several variables is something that is like f of x, y, instead of having f of x, or instead of having g at x, such functions. So now our functions have more than one independent variable. So usually this is motivated in financial mathematics as, let us say that you are trying to calculate the insurance premium, okay, for a month. So there are things that you take into account. So let's say, for example, that you take age into account, and age, you call it X, and you consider other variables such as the gender of the client, so Y, and other variables. Okay, so let's say that f of xy represents the function that calculates the monthly premium of a certain insurance, where x represents the age and y represents the gender. Obviously, there are other factors that are taken into account. Okay, so these are the type of functions that we will be looking at. And the idea behind partial differentiation is we will be trying to find derivatives of these functions. And by partial, we mean that we will be finding derivatives with respect to x. Remember that this is a function of x and y, but rather we will be finding partial derivatives with x while we do not consider y, or find the derivative of y and then we do not consider x. So it's such derivatives that we'll be looking at. So let us look at the definition. A function f of two variables is a rule that assigns each ordered pair of real numbers x, y in a set D to a unique real number denoted by f of x, y. So what you had with functions or of one variable or of a single variable, you were looking at f of x, right? And the value that you considered was just x. That is the value that you plugged into the function in order for you to get the y value, which was given by a certain rule f. Here, instead of having just the x value, we have the xy value. So we call that an ordered pair. By ordered pair, it means that we start with x, then y. We do not have y, then x, okay? It is emphasized by the ordered pair of x, then y. You will see just now when I do an example. So then the set D is the domain of f, and its range is the set of values that f takes on. Okay? We note that we often write z is equal to f of xy to make explicit the value taken by f at the general point xy. Now, what did we do with the function of one variable? We had that y is equal to f of x. And then that's why we were finding derivatives as dy dx. Here, you see that we will be finding derivatives as dz dx and dz dy. Okay. Then, the next thing. So, graphically, what I am talking about is that this definition, what it means, we have a set D, okay, which is the domain of the function. And we have an ordered pair. Let's say it's contained in the set. Let us call this AB, okay? So then it maps because of the rule to a certain value, and this value is what we call f of AB. Okay, so it's with what we call the y value on the y-axis. But here we do not actually have the y-axis. Yes, we do have the y-axis and the x-axis, but this is actually a 3D graph or a 3D function, which has the x-axis, the y-axis, and the z-axis, which looks like this. Okay, so that would be x, y, then z. Okay, and say another point, let us call it CD. Then when it maps, because of the rule, it maps to the z value, and the z value there is f at CD. Okay, so now let us calculate f at 3, 2 if the function is given by this. Remember, what did I say? We said that it is an ordered pair, and I emphasized that we start with x then y. It then means that the value that we will be substituting into the function for x is 3, and the value that we substitute into the function for y is 2. So f at 3, 2 is equal to the square root of x, which is 3, plus y, which is 2, plus 1, divided by x, which is 3, minus 1. So then this is the square root of 6 over 2. Okay, then we move on. We still calculate f at 3, 2. If f of xy, this is the function, is given by x ln y squared minus x. So let's see how do we do it. So we find f at 3, 2. Remember that x is 3 ln y, which is 2 squared, minus x, the x value, which is 3. So then this is 3 ln 2 squared is 4 minus 3. So then this is 3 ln 1. And we know that ln 1 is 0. Okay. And then something else is determine the domain of such a function. Even with several variables, the idea behind the domain is still the same as what we did in the past. Here we have a radical in the numerator, and then we have a certain function in the denominator. So we know one thing is that we cannot divide by 0. So what does that mean? It means that we know that x minus 1 should never be equal to 0. And what else? And we know that whatever that appears inside the square root sign should be non-negative, meaning x plus y plus 1 should be greater than or equal to 0. And then you solve. This means that x should not be equal to 1, and this means that y should be greater than or equal to minus x minus 1. So therefore, the domain of f is the set of the values x, y, such that y is greater than or equal to minus x minus 1 and x is not equal to 1. Okay, so that is how you determine the domain. Next, a function f of two variables is called continuous at AB if the limit as xy approaches AB of f of xy is equal to f at AB. Let me just quickly recap the definition of a continuous function of a single variable. We said that a function f of one variable is called continuous at A if the limit as x approaches A of f of x is equal to f at A. So now look at the difference. We are looking at two variables and we are taking a certain point. And that point is AB. It is a pair. Okay? So then the limit no longer becomes the limit as x approaches A, but rather the limit as xy approaches not just one thing, it must approach an ordered pair, AB, of the function should be a function of several variables of f of xy. And then this should be equal to f at AB. Although here we do not get too much into continuity, but I'm just trying to show you that the idea is still the same even when you extend the axis. Instead of working with 2D, you work with a 3D shape, okay? So now we get into the differentiation part. So we say that if f is a function of two variables, its partial derivatives are the functions f subscript x. So it is not fx, it is f small x there. So we put it as a subscript. And not fy, it is f subscript y. They are defined by, so remember that you cannot take the derivative of xy at the same time. You take x on its own and you take y on its own. So when you take x on its own, let us just quickly recall once again the derivative definition. It is f prime at x is equal to the limit as x approaches, as h approaches 0 of f of x plus h minus f of x divided by h. Right. So here, what do we have? Look at what is happening with when you take the partial derivative of f with respect to x. You change that. You put x plus h on the first part of the function, and then you keep y minus f of x. Now our function is f of xy divided by h. And then when you're trying to find derivatives with respect to y, it means that you are not considering x. So therefore, you take it as the limit as h approaches 0 of f of x y plus h, because you are considering the partial derivative with respect to y. We call them partial derivatives, not derivative, okay? So then there is a certain notation that we use when we are trying to find partial derivatives. So let me just quickly take you to the one-dimensional or the 2D problems that we did. We had that if y is equal to f of x, then how did we find the derivative? The derivative was dy dx, or we wrote it as df dx, or we wrote it as f prime at x. So here, instead of having f prime at x, we have f subscript x, which says that we are finding the derivative with respect to x. So now look at the notation. Instead of writing the dy dx, we have a partial z partial x. So the derivative sign looks like a 2 here. It's just that you do not take it to the other side. Okay, so that is how we write the d now. It's a partial to show that we are finding the partial derivative. And remember that z is equal to f of xy, which means that you can write this as partial f over partial x. So you are finding the derivative of f with respect to x, but you are emphasizing that f is a function of several variables and you are finding the derivative with respect to x alone. Okay, now what happens with y? The same thing. The function z is equal to f of xy. So that means that when you are finding the partial derivative with respect to y, it means that you are trying to differentiate partially the function z with respect to y. Or in this case, it is the partial derivative of the function f with respect to y. That looks like a 2. Okay, so if you do this, df dx, I give 0. If you do partial f dx, I give 0. Okay, so be careful of notation. It speaks volume here. Okay, so then there is actually a rule that we are using to finding these partial derivatives for such a function. So look at it. I put it as NB, meaning that it is very, 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 very important. So to find the partial derivative with respect to x, you regard y as a constant. And then you differentiate the whole function. WRT means with respect to x. Okay? So if you have, for example, f of xy is equal to x squared y, and I'm saying that find the partial derivative with respect to x. So this is fx. This is the partial derivative with respect to x of xy. I say that consider y as a constant, meaning make y look like a number. Recall this. If you had to find the derivative of f of x is equal to x squared, let's say 7, what would the answer be? F prime at x would be equal to 7 multiplied by the derivative, right, of x squared, which is 2x. So that is the exact same thing that you do when you are finding the partial derivatives with respect, in this case, to x. So you look at that y as if it's the 7. So you keep it as it is. So you have y. And then you find the derivative with respect to x. So then that is 2x, which means that the answer becomes 2xy. Okay, so now let us see what happens if you have to find the partial derivative of the very same function with respect to y of xy. Okay, so what you do, the rule number 2 says to find fy, you regard x as a constant. So this means that now this one, okay, so now it means that this one is a constant, meaning you keep it as it is. So you have x squared, and then you differentiate with respect to y. And what is the derivative of y with respect to y? It is equal to 1. So then the answer becomes x squared. So let us see. Let us look at an example. If f of xy is equal to x cubed plus x squared y cubed minus 2y squared, find fx and fy. So find these two partial derivatives. So to find the partial derivative with respect to x of xy, this is what we do. We consider y as a constant. So let me just rewrite the formula here. F of xy is equal to x cubed plus x squared y cubed minus 2y squared. So this is how I'll be doing it for now, just to get the idea across. Since we want f of x of xy, okay, this is what happens. This, remember, the subscript, instead of having f prime at x, this is now a function of two variables. You say, I am taking the derivative with respect to x of xy. So it is important to write it like this. There should be no primes here. Okay, so we do not have prime anymore. Right, so what I'm trying to say now, let me get back my highlighter. So we are finding the derivative with respect to x of this function of several variables. So that means that we consider y as a constant. So if we consider y as a constant, I'm going to highlight the y and treat y as a number. So where is y? This is y, and this is another function of y. So it means that those ones, I consider them as constants or as numbers. And then I find the derivative. So what is the derivative of x cubed? It is 3x squared plus Remember that y cubed, I treat it as a number. So it means that I write it there as it is. And then I find the derivative with respect to x of x squared. And then the derivative of x of x squared with respect to x is 2x. And then what is the derivative of minus 2y squared with respect to x? Remember that since it's highlighted, we are treating it as a number. And what is the derivative of a constant? The derivative of a constant is 0. So minus 0. So then this is 3x squared plus 2xy cubed. Okay, now let us find then the derivative with respect to y. So what happens now? Now what we are going to do is to treat the x coefficients or the x variables here as constants. So that means that we highlight all the x's. We are now going to treat them as numbers. Okay, so let's find the derivative. What is the derivative of x cubed with respect to y? It is highlighted, so it means that it is a number, so it's 0. And then x squared is a number, okay? Then we find the derivative of y cubed with respect to x. And the derivative of y cubed with respect to x is 3y squared. And then we find the derivative of minus 2y squared with respect to y, and we get minus 4y. So to simplify, we have 3x squared y squared minus 4y. Now, if f of xy is equal to 4 minus x squared minus 2y squared, find fx at 1, 1 and fy at 1, 1. So I'll do one of them and then you do the other as homework. So to find fx, remember what do we do? It means that we treat y as a constant. So it is like this. Y is treated like that 4 over there. So then what is the derivative of 4 with respect to x? It's 0. The derivative of minus x squared with respect to x is minus 2x. And then we find the derivative of minus 2y squared with respect to x, which is 0. And therefore, f of x at 1, 1 is equal to minus 2. And wherever we see an x and whenever we see a y, we put 1. So then the answer is minus 2. So I want you to try out f at y. And then at 1, 1, you will get that the answer is minus 4. Okay. So let us continue finding another one. So recall chain rule. What happened with chain rule? So if you had to find the derivative with in chain rule, what did we do in chain rule? In chain rule, we had to find the derivative with respect to x, let's say, of f at g of x. So we called it the composition of a function. So what we did is to find the derivative of the outer function, evaluated at the inner function, multiplied by the derivative of the inner function. Right. So this was chain rule. Okay. Now let us see if can we do chain rule with partial derivatives. So what happens if f of xy is sine x over 1 minus y? We need to calculate the partial derivative with respect to x and the partial derivative with respect to y. So let us recall chain rule. What does it say? So the outer function here is f. The outer function f is sine, and the inner function g is x over 1 minus y. But what happens is that we now have a function of several variables. So the idea is still the same. So to find the partial derivative of f with respect to x, we first find the derivative of the outer function. And the derivative of the outer function, sine, is cos. We evaluate it at the inner function. which is x over 1 plus y, multiplied by the derivative. So we take the partial derivative with respect to, in this case, x, of the inner function. And what is the inner function? It is x over 1 plus y. Okay, so let us just see how can we simplify what we just have there. So we have 1 plus y. So we are trying to differentiate with respect to x. Remember that in this case, this is where I would write d dx. So now, instead of writing d dx, we write partial over partial x of, this is x, 1 plus y to the power minus 1. Okay. Now, so this is cos x over 1 plus y. Now, the partial derivative with respect to x, this is a function of several variables. So the derivative with respect to x here is what we are going to find, while we treat any other thing as a constant. So that means that the derivative with respect to x is equal to 1. So then we have 1 times, that thing is just a number. What is highlighted, we treat it as a number. So then the answer is cos of x over 1 plus y times 1 over 1 plus y. Okay. Now what happens if you have to find the partial derivative of f with respect to y of this function? Once again, you have to find the outer derivative, which is cos at the inner function, which is x over 1 plus y, multiplied by the partial derivative. Remember, it is with respect to y of the inner function. And we know that the inner function can be written as, it can be written as x multiplied by 1 plus y to the power of negative 1. So what happens now? Remember that since we are trying to find the partial derivative with respect to y, it means that we treat x as a number. Okay? So that means that this is equal to cos of x over 1 plus y multiplied by, since x is a number, we keep it there, and then let us now find the derivative. We see that here we have to apply chain rule with power rule, because our variable of interest which we are differentiating with is contained there, which is y. So then how do we differentiate this one? It becomes minus 1 plus y to the power negative 2 multiplied by the derivative of the inner function y, which is equal to 1. Okay. So then this is cos x over 1 plus y times, this becomes minus x over 1 plus y, all of it squared. Okay. So just to simplify further, perhaps we can write this as minus cos x over 1 plus y times x over 1 plus y, all of it squared. So that is how we find the derivative. Now let us just, once again, what we have done in the past, we continue doing it again here. Now what happens if we reach implicit differentiation? So we need to find partial z over partial x and partial z over partial y if z is defined implicitly as a function of x and y by the equation which we have there. Remember that if we are trying to find the derivative of a function that is defined implicitly, in our case it used to be dy dx, okay, where y was defined implicitly as a function of x, but then we kept in mind that it is written as a function of x, okay? So in this case, what happens is that z is defined implicitly as a function of x and y. We do not know what they are, but what we know is that it is there. It is written implicitly, okay? So let us first find dz dx. So what happens? Partial z, partial x, right? So what happens there? Remember that the first thing that we used to do, we made it clear that to find partial z, partial x, we differentiate both sides of the equation by, in this case, x. So what do I mean? It means that we take partial x. Remember that is where we would write d dx of whatever is equal to d dx. So remember that to emphasize that this is a function of several variables, we use partials. So of x cubed plus y cubed plus z cubed plus 6xyz is equal to partial x of 1. That's what we do. Now let us then find the partial derivatives. Let's first remember something. We are finding the partial derivative with respect to x here, and whenever we see a y, then we know that y is a constant. So y is a constant, there y is a constant. Z is a function of x and y that has been defined implicitly. So we do not treat it as a constant. Okay. So what does it mean? So to differentiate x cubed with respect to, remember that the rules that held in the past, that the derivative of f plus g is the same as finding the derivative of f plus the derivative of g. The rule still holds even here. Okay, so that means that it is 3x squared. Y cubed is now considered as a constant. Remember that z is a function of x and y, which is defined implicitly, which means that we take the derivative of z cubed, which is 3z squared, but we keep into account, or we take into account the fact that z is an implicitly defined function. So that is where in the past we would write it as dy dx. Now we write it as partial x, partial y. Plus, now look at this. 6y is actually like a constant, okay? And then we have to find the derivative of xz, which means that we apply product rule here. So if we take 6y first, then 6y is now my new constant here, and then I have to differentiate first with respect to x, which I get 1z, plus now I keep 6xy, and then I have to find the derivative of z with respect to x. The derivative of z with respect to x is 1, but then I keep I take into account, or I keep in mind, the fact that z is an implicitly defined function, so then it is partial z, partial x, which is equal to 0, okay? So that means that I have 3z squared partial z, partial x, plus 6xy, partial z, partial x, which is equal to minus 3x squared minus 6yz. Remember that this was the goal even in the past, that we want to have the dy dx's on the left-hand side and then take all the other terms on the y, so that we factor out partial z, partial x, and then we have 3z squared plus 6xy, and then this is equal to minus 3x squared minus 6yz. Then the partial of z with respect to x is minus 3x squared minus 6yz over 3z squared plus 6xy. If you want, this is equal to minus x squared minus 2yz over z squared plus 2xy. Okay, so now I want you to attempt the same thing, but for partial z, partial y, and your answer should be minus y squared plus 2xz over z squared plus 2xy. Okay, now let us see what happens if we have higher derivatives. So if f is a function of two variables, then its partial derivatives fx and fy are also functions of two variables. That is what we saw just now. Okay? What does it mean? It means that if we have f of xy, let me think of a function x cubed y squared. So if we find f of x, xy, then the answer is 3x squared y squared, and fy is x squared y, and then we have this, right? So look at that. So we say that if f is a function of two variables, so there it is, f is a function of two variables, then its partial derivatives, which are these two, they are also functions of two variables. We see they, even here, that's the case. So it means that we can then consider their partial derivatives. Okay? And take note how the partial derivatives are like. So we have the partial derivative of f of x, which is, or rather the partial derivative of x with respect, of f with respect to x. Okay, so that function, because it's a function of two variables, we can differentiate it either with respect to x or with respect to y. And then fy, f subscript y, is also a function of two variables, which means that we can differentiate it with respect to x, then y as well. So then these are what we call the second partial derivatives, or the second order partial derivatives of f. Now what happens if, for notation purposes, what is happening exactly with this notation, fx x? It means that we are taking the derivative with respect to x of a function. Remember, how can we write fx? It is df dx, right? Which then we can write it as d squared f over dx squared. Or, well, in this case, since it is z, we can also write it as d squared z over dx squared. What do I mean? Remember that with second derivatives, this is what we use to write. So the notation is still the same. It's just that now we are using partials. Okay. Now what happens if you have fxy? It means that you are differentiating with respect to y the partial derivative of x. Okay. So this means that you have, this is the second derivative of f, which is equal to partial y, partial x. Okay, or if you want, you can write it as partial squared z over partial y, partial x. Okay. And then for this one, it means that you have partial, the partial derivative of x, which you are taking the partial derivative which has been taken with respect to y, so then it is partial squared f over partial x partial y, or it is partial squared z over partial x partial y. And then this one is the partial derivative of y, which has already been taken with x, so it is the second derivative of partial squared y, which is partial squared z over partial y squared. So what does this thing mean? So if you have fxy, now this is basically this one. I have removed the brackets. It means that we first differentiate with respect to x, then with respect to y. Whereas if you have fyx, it means that you first differentiate with y, and then you differentiate with respect to x. The order is important. Okay, the order is important. There will be a theorem that gives us the go-ahead to say it doesn't matter. Okay, but Till then, the order is important. You first find the derivative with respect to x, then y, or y, then x. Okay. So let us see. Find the second partial derivatives of the following function. So we first need to find the first derivative, okay? The first derivatives. And then from there, try to find the second derivatives, okay? So let's see. The first derivative is fx of xy. So that means that we are considering x's only, and everything that is y is taken as a constant, okay? So we have 3x squared plus 2xy cubed. This is the function that we've already differentiated in the other example. And then fy at xy is 3x squared y squared minus 4y. So now let us find fxx. Now, just in case you do not know what to do here, this is what I suggest you do. Okay? Put in brackets here. It means that you have to take the partial derivative with respect to x, that is the outer part, of this. Okay? So now let us substitute in. So it means that we are differentiating 3x squared plus 2xy cubed. And now if you differentiate this, you get 6x plus 2y cubed, because y cubed is treated as a constant. And now what happens if you are trying to find fyy? Remember, you put in brackets there. So it means that you are finding the partial derivative with respect to y of what we have there, okay? So it means that you first find the partial with respect to y, and then you differentiate it again. So you put fyy. So these brackets, you can put them as something to tell you how to go about with calculating the derivatives. Okay, so it means that we have the partial with respect to y of 3x squared y squared minus 4y. So this is equal to 6x squared y minus 4. So if I ask you to find the second partial derivatives, it means that I want f of xx, f of x of yy. You are not done there. Remember that these functions have their own second derivative. So you still need to calculate two more derivatives, which are fyx and fxy. Now, how do you go about calculating fyx and fyy and fyx? Once again, this is where the brackets are important. You put the brackets there. So what does it mean? It means that you are finding the derivative now with respect to x of what you have already differentiated with respect to y. And this one says you are finding the partial derivative with respect to y of what you have already differentiated with respect to x. So this means that you are finding the partial derivative with respect to x, and then dfy means it is this function there, which is 3x squared y squared minus 4y, which is equal to 6xy squared. And then if you do it for this side, you have the partial with respect to y of 3x squared plus 2xy cubed. And then you get that the answer is, remember that 3x squared, because we're differentiating with respect to y, it's considered as a constant. So then that answer is 0. And then here we have 6xy squared. I want you to take note of something. These two are the same. Okay, so let us note that fyx of xy is equal to fxy. So what are the conditions? Because we see that we actually do not have to calculate the derivatives all the time. We do not need to do 4 derivatives. If we can do fxx, fyy, and then if we can do fyx, then we do not need to find fxy. What is happening there? Then that is when we have what we call Clairaut's theorem. Clairaut's theorem says, suppose f is defined on a disk D that contains the point AB. If the functions fy and yx are both continuous on D, then fxy and fyx are the same in that domain. Okay, so this is just talking about the domain of the function. We're just calling it a disk at the point AB. Okay, here you are not really to worry too much about the disk and so forth. And then you also just need to remember what a continuous function looks like, okay? You do not need to worry about the definition of continuity, but I've already stated it here. So verify that Clairaut's theorem holds here. If f of xy is equal to exy sine y, so what do? You first need to find the partial derivative f with respect to x. So if you do that with respect to x, it means that you are taking the derivative. Remember that you keep sine y as a constant. So sine y is a constant. And then ey, it's also like a constant. So it's like you're finding the derivative of e to the power of 7x. Right. And then what is the derivative of e to the power of 7x? It is the derivative with respect to x of e to the power of 7x. Remember that it is like finding d dx of e to the power of f of x, which is e to the f of x times f prime at x. So then it would be e to the 7x times x. Times 7. Okay. In this case, what do we have? Sine y is our first constant. So we have e to, we keep the function xy multiplied by the derivative, right? We have to multiply it with the derivative of the top function. And then the derivative of the top function is y in this case. Remember that we consider x as a constant. So then the answer is y sine y e to the xy. Okay. That's the first thing. Then the next thing that we do is to find the derivative with respect to y, partial f, partial y. So once again, what happens here, you have, in this case, it is going to be a product rule because e to the x has a variable y and sine x has a variable y. So then it becomes exy times the derivative of the top function, which is x, right? Because we consider x as a constant, right? Sine y plus, this remember is product rule. You keep the first function and you multiply and you find the derivative of the second function. Right, so this is what we have. Okay, now what is then, because we are trying to verify Clairaut's theorem, we need to find f of xy and we need to find f of yx. What is f of xy? Remember, you put the brackets here. This means that you need to differentiate with respect to y what you have already differentiated with respect to x. So it means that we are finding the partial derivative with respect to y of y sine y exy. So remember, this means that you have to do product rule 3 times because you have y sine y exy. So y appears 3 times. And then here, what does it mean? This means that you have to find the partial derivative with respect to x of what you have already differentiated with respect to y. So this means that you have to find the partial derivative with respect to x of exy, you can put that x there, sine y plus exy cos y. Okay, so I'll just do one of them. You need to verify that these derivatives are equal. Okay, so remember that since we are doing product rule 3 times, I'm first going to differentiate this one and then consider the others as constants. And then I differentiate that one and consider the others as constants. And then I will end off with that one and consider the rest as constants. Okay, so let's differentiate the first one. So if you differentiate y, the answer is 1. So that means that I keep sine y, exy. Those are the functions that I keep. And then plus, now I differentiate cos, this is product rule. It's cos y multiplied by y e to the power of xy. Right, so then I keep those ones. Plus, now I keep the rest, which is e sine y, the two first functions, and then I differentiate the last function. And with respect to y, it is e to the x y. And remember that we consider x as a constant, so then the answer is, we have to keep it with x there. So then the answer, just to clean it up, is exy sine y plus ye xy cos y plus xy e to the power of xy sine y. So now I want you to verify that if you find this derivative, you get that as well. That is how Clairaut's theorem works. And then this one, you also need to do the same thing. Here, remember that what you have to do is to write ln as this becomes x squared plus y squared to the power of a half. And then you find the partial derivative of u with respect to x. Then this is 1 over the function multiplied by the partial derivative with respect to x. Remember that this is chain rule of x squared plus y squared to the power of a half, right? And then this becomes 1 over the square root of x squared plus y squared times. Now let us differentiate this one. Remember that what do? We do product rule. And remember that since we are differentiating with respect to, we do chain rule. And remember that since we are differentiating partially with respect to x, it means that we consider y as a constant. So we bring the half to the front, we keep the function as it is, and then we subtract 1 from the numerator, multiplied by the derivative of the inner function, which is 2x. Okay, and then this simplifies to, I have 1 over the square root of x squared plus y squared. The 2's cancel, so I have x over, this becomes x squared plus y squared. Okay, so then I'm multiplying these two together, and remember that a over b times c over d is equal to ac over bd, which means I have x over the square root of n times the square root of n is just n, so I have x squared plus y squared. Now, to find the second derivative, you'll have to differentiate this one now with respect to y, and then you'll have to differentiate the y one with respect to x. So then the same thing applies for du, dy, and I got y over x squared plus y squared. So then now your duty is to find the other derivatives and show that indeed the derivatives with respect to xy and yx are the same. That is what Clairaut's theorem does. So you should be able to complete section 3.1 and 3.2, the exercises thereof, from the notes. Thank you.